And we wanted to answer these questions. Default setting is default setting perfect for all sites. And when we have to change the configuration, what is the top boundary conditions in the WinSim and different turbulent model in the WinSim. The refinement area, size and buffer, what is the size and what we can use for size and buffer. When to use smoothing and grid size, solvers and stabilities. Okay, as you know, we have some default setting when you install the WinSim desktop. But this default setting is, the question is this default setting perfect for all the sites? Absolutely not. This default setting can be used for many sites, but for different sites, we need to change and use different settings for turbulent models, top boundary conditions, forest model, or other options we have in WinSim. It depends on your site complexity. For example, if there is a forest model, you can use forest model to shift up the vertical profiles and or create more turbulent movements. And for example, there are several top boundary conditions. We are going to review this in the next slides. Okay, next question is, when should we start tweaking models? First of all, when we have a non-convergence, we can try to change some configuration in the model to get a convergence. But many factors can create this non-convergence, and it depends on different case can show different problem regarding a non-convergence issue. In complex terrain, our suggestion is you can increase the resolution of the grid cell, or even use coarser grid for reaching the convergence. Sometimes the vertical profile are not matched with the observation. Then we can work on some other configuration except default configuration, and try to turn on the forest, or try to use the atmospheric stability in WinSim to get a better convergence solution. For top boundary condition, we have three different top boundary condition in the WinSim: fixed pressure, non-friction wall, and diffusive link. Fixed pressure is good for complex terrain. If you have a complex terrain site, it's better to use fixed pressure. Two other top boundary conditions is appropriate for flat or simple terrain. Non-friction wall can be used for flat terrain. It makes sure the momentum is maintained in flat terrain. Diffusive link is a moving version of the fixed pressure and can be used for the flat terrain also. For turbulent model, there is three option. Okay, to force option, because standard K epsilon model and modified K epsilon model is the same, but with different parameters. K epsilon model is widely used, and but is not appropriate for complex terrain with pressure gradient, severe pressure gradient, and flow separation. K epsilon produce very large vertical mixing, and yeah, this is the issue of the K epsilon. Then we have modified K epsilon. Modified K epsilon is K epsilon, but with different constant or parameters in K epsilon formula, and it produce the less mixing lengths, and can be more appropriate than standard K epsilon. But two other options, K epsilon RNG and K epsilon with YAP correction. These two options is appropriate for flow separation and complex terrain, and based on our experiment, RNG is the best regarding the convergence behavior. Okay, for refinement area, how much refinement area we have to consider when we are trying to define our model? The recommended buffer area is 10 kilometer at each side, but it can be more for offshore and when we have a stable atmospheric boundary layer. And when we are trying to define a refinement area, we have to consider the border from our climate files must be 1 kilometer away from the border of the refinement area. This is the just recommendation we can consider for defining a grid size and buffer area. The next question is when to use the smoothing. Okay, the smoothing is not recommended in default cases, but when we have a non-divergence issues in some case, we can try to use smoothing. In the smoothing, we can try at first with the factor of the in order of the 0.1. It depends on the second order of derivative in your train. Look at that and select the smoothing factor. Then if divergence again occurred, you can decrease it with lower derivative second order derivatives. And for smoothing, we have two options, inner and outer option. Inner can smooth the domain from the center to the radius. The radius we define in the model, and the outer can be used for smoothing the domain from the outer part of this radius. When you set the radius, if you set the higher radius, it will start smoothing from the borders of the domain. Okay, grid size. When you are trying to define a domain, grid size is important, and at first you have to, if you are using the desktop version, you have to consider your hardware resources, CPU, RAM, then decide which grid resolution is good for your PC or your server. But the recommended resolution is 10 to 50 meter for most of the cases. For a complex terrain, you can use the higher resolution also. Regarding the number of the vertical layer, 25 to 30 vertical layer is almost enough for flat terrain, but when you increase your grid size, it's better to increase your grid layer, vertical layers also. When you are defining your vertical layer, it's better to just consider the distance of the thickness of the first at least three layers from the bottom. The three of the layers should have roughly the same thickness. For example, in this table, you can see the seven layer has this thickness of the 5 meter. We recommend to define the number of the layer with at least 3 layer with the same resolution. Okay, for solvers, there are 3 or 4 options in the WinSim desktop. Based on our experiment and sensitivity analysis, selecting a solver depends on your configuration and your size of the grid or your case. G solver is the best in terms of the convergence, but for big project, more than 4 million cells, parallel GCV AMG can be faster in terms of time. But selecting the solvers depends on several factors like terrain complexity, turbulence model, boundary conditions, and other things you have to consider. Maybe sometimes when you select a solver with the different turbulence model, the solution can be faster and you can get the faster solution or better solution. You have to consider this combination of the configuration also. Regarding stability, when it is useful for considering the stability, it's better to at first analyze your observation data and your measure scale data also to see is there any stable condition in some sectors or not. If you wanted to use the stable case run in WinSim, the Monin-Oberhof length should be more than 50, and we cannot define a negative Monin-Oberhof length in WinSim. Here in this figure, you can see in some sectors the stable condition is dominant, and for some of them is neutral, and the stable run WinSim run can produce a better vertical wind profile. Okay, this was the recommendation for running the WinSim, and I hope it helps you to get a better result, faster result, and complete your project faster.
Right.
Yeah, thank you.
Thank you. I want to just check in